Yeah, I didn't intend to do this until I had a cup of coffee this morning, and I don't normally have coffee, and here I am holding a microphone. Last time I held something like this, it was karaoke night at the Lava Lounge, but I'm not going to repeat that performance here. Instead, I hope to make a case that ground-based gravity measurements might be something that this community should get involved in. I've been trying to get the USGS volcano program into gravity for a while, and these are the sorts of things I run into from the leadership committees. That the water table obscure any volcanic signal. You'll never be able to account for instrumental drift, and the short answer to these is that that's total garbage. We can get around these problems, and in fact gravity offers a lot of insights that other techniques just don't. And so what I hope to do in the next 4 minutes or so is share some of these results from Kilauea, from campaign and continuous results collected with a collaboration of Maurizio Battaglia and Daniele Carbone, and try to share some of these unique things that gravity can bring, and then how we might as a community utilize these results. So at Kilauea, we have a nice gravity network for campaign measurements. There's 45 sites centered around the caldera, which is the round area in the top. We can survey these sites with CG5 gravimeters, thanks to the stimulus package that was passed a few years ago, and we've surveyed these with other instruments over the last 5 times since 1975. For example, in the south part of Kilauea caldera, over the main magma storage area, you can see that subsidence in the solid lines has gone 2 meters between 75 and 03, but the gravity has decreased not that much at all, suggesting that it's not just mass change that's driving that subsidence. In contrast, over a shallower magma body in the center of the caldera, subsidence but gravity increase, which suggests in fact that mass was accumulating in void space, which is not a result that you would have gotten with deformation alone. You really needed gravity to get to that conclusion. Gravity campaign measurements have been done at all sorts of volcanoes, and in fact in many places have helped to determine whether or not the driving forces of unrest is magmatic or driven by hydrothermal, and when combined with deformation, you sort of get the ultimate monitoring tool. We also do continuous measurements at 2 places at Kilauea Summit, right on the rim of Halemaumau crater above the active summit vent, and near the Hawaiian Volcano Observatory, which is located right there in the middle. And we find we can track lava level variations in the summit vent, which you can see in that picture down there, very well. On March 5th of last year, there was a drainage event as magma drained the summit to feed a fissure eruption. That top bar there is the drainage, and the red is the gravity value that tracked that drainage. We've also seen rise and fall cycles. The 2 webcam images show you the level of lava, and you can see that before and after, there's a small drop in gravity associated with a drop in the lava column. We can do some back-of-the-envelope calculations for those 2 examples, and we find that the amount of mass lost based on the gravity is a lot less than what you would expect for a normal magma density. So it seems that these magma, the magma in the summit vent might actually be made of a foam, which has some very interesting implications for volcanic degassing. We can also look at the frequency components of this signal, and we find that there's actually a 30-second component that matches VLP seismicity, but there's also a frequency component at about 150 seconds, which does not appear in the seismic record. And that component may actually be due to small-scale convection currents in a magma storage area. That's about where that yellow dot is, based on the correlation between the measurements at the 2 continuous gravimeters. So these are, again, things that we would not have seen in any other way if we didn't have gravity. Now, of course, volcanoes are not the only applications. They happen to be the ones I've spent the most time about, but 2 other ones that I know of right off the top of my head are that they're monitoring groundwater recharge in Tucson with gravity. And in Europe, they're looking at water levels in karst topography, where actually that's a lot of their drinking water comes from karst, so it's very important to know where those things are. So that brings up another point, and I think we heard that very well in one of the sessions this morning, that one person's noise is another person's data. What if you want to measure hydrologic properties? If you can see it, fantastic. So some of the barriers we face to developing gravity: 1, it's expensive. New instruments cost over $100K. Upgrading old instruments is $25K. And there's a lot of technological challenges. These things are power hogs. It's hard to keep them level. So there's a lot of things to overcome, but I think if we're creative about solving these problems, we can actually get a lot of use out of gravity. In technology, new instruments are being designed all the time. This is the iGrav, because everything new has to have a small I in front of it. It's got very low drift rate. It deals with a lot of the problems we have. It's obviously not field portable, but it's on the way. For expense, you ever have one of those in the basement of your department? Lacoste and Rauberg G meter that can be upgraded with perhaps community resources to turn into a continuous gravimeter. So there are ways as a community that we can come together to solve some of these issues. And I think UNAVCO even though it was the University Navstar Consortium, it is about far more than just GPS, and now we can maybe add LiDAR to that list. There may also be a case for gravity in here as well, and hopefully 20 years from now, somebody will be giving the Ignite talk like Christine gave about GPS, but for gravity. Thanks.